Hi everyone. So today I'm not going to talk about scikit-learn, but more about a recent trends in applied machine learning, which is the move to neural networks for building recommender systems. So first, let's talk a bit about recommender systems. So the canonical example of recommender systems is product recommendations. So for instance, on an Amazon website, if you pick up a book, if you go on the page of a specific book, so this is the scikit-learn book by Andreas Müller on machine learning, automatically Amazon will generate two groups of recommendations, one for stuff to put in addition to your basket, and another group for additional books you might be interested in if you want to change your mind. So here the goal is clear, is just to increase the sales, to do upsells, and so on. It's also used for recommending media. For instance, on a music streaming platform such as Spotify, you have an input in green, which is my profile. And as an output, the recommender system will generate a playlist that is tailored to my listening habits. But it's making it possible to discover new music, because none of those bands there, I don't know any of them, but there is a good likelihood that it's actually a good playlist when I go to work. So here the goal is to reduce UI friction, to simplify navigation, and to increase user retention on the platform, but also to hide holes in the catalog. Because suppose if you had only the search engine as a UX, as a user experience to access the content, it might happen from time to time that when I type the name of a band, it's not in the catalog, and then I'm disappointed. If you push stuff that are more likely to suit my taste, then you can effectively hide this by reducing the occurrences of such disappointment. So it's actually good for increasing the revenue of the platform as well. And other applications of a recommender system that is not as trivial is actually search engines. Nowadays, search engines, when you do a query, for instance on Google, you have two inputs. You have the keywords that you put in the search field, and you also have your personal account, because you're logged in most of the time. And then you get the output, the web pages that both match your profile and the keywords. And in that case, the keyword is Python. And what I get as first result is not the animal, it's not the snake, it's the programming language. And actually, if you scroll down, there is no snake at all on that page. So it's really, really personalized. And the second recommender system that you get on that page is actually the ads. It's also personalized based on your clicking habits. So this is really important from a business point of view, because this is the main source of revenue of two of the largest global companies in the world. So you can see that recommender systems nowadays have a really, really big impact. And I didn't speak about personalizing social network status messages like in Facebook or Twitter and so on. So let's talk a bit about the concepts behind recommender systems, now that we know what they are good for. As we've seen previously, there are two kinds of recommender systems based on the input data that we feed to the system. First, there are content-based systems that take a description of the user, like it could be the age, the gender, the geographical location, and description of the item, like metadata. For instance, if it's a movie, the words that appear on the title, the picture of the cover of the movie, or the name of the director, the publication date, the language of the movie, and so on. And there is another kinds of inputs that you can use, is not the description of the items, but the interactions between users and items. In that case, we just represent the users and items as integers, identifiers, in the catalog and the user base, and we just count the number of times one user is interacting with one item. And the kind of interactions can be of several kinds. They could be stars, number of plays, number of likes, number of comments, number of clicks in search results, and so on. So in that case, we aggregate a lot of data based on the user activity, basically. Finally, there are also hybrid systems that kind of mix and match the two kinds of input into the system. And this is interesting because typically when you have a new item, a new movie, for instance, you don't have any clicks on it yet, so you're not able to recommend it. So in that case, we have the cold start problem, so it's good to use the description of the name of the director to make a good prediction, to recommend it to the right users. But once a movie or a user gets a lot of activity, you get a lot of data, and it's good to leverage it, and then collaborative filtering tends to yield higher performance. There is also two kinds of targets. One is explicit feedback, where you have negative or positive feedback and something in between, for instance, when you give ratings using stars. And the other one is implicit feedback. In that case, you don't ask the user to give an explicit feedback because it's too costly, it's a pain in the user experience. But you just record whatever is happening, and you consider that all the clicks and all the interactions between a specific user and an item are positive. You can filter out some negatives, like for instance, when a user starts to listen to a song and stops 10 seconds after the start, then you can remove that as a positive, but you keep all the other events as positive feedback. And in that case, you can evaluate the quality of your prediction by ranking items and making sure that positive items are ranked above the negative items that are sampled at random in the database, all the other items. So the traditional way to do collaborative filtering is to use a mathematical model which is called matrix factorization. You have a big sparse matrix of all the data, which is called R in this diagram. The rows of this matrix are the users, description of the users. The columns are the description of the items. And the entries are the ratings or the number of plays for a specific user for a specific item. And so one user will see only like less than 10% of your catalog, or buy 10% of your product. Otherwise, you're very lucky. So this matrix has a lot of missing entries. And so the goal is to predict the values for the missing entries, and we can do that by doing the product of two smaller matrices that are actually the model parameters, U and V, and they are d-dimensional space to represent the users and the items. So by doing the dot product of one row and one column, you get an estimate of the ratings. And you can obtain the good values for those parameters by minimizing a loss function using gradient descent, like least squares, using a stochastic gradient descent, and so on. So this is the traditional way to do it. If we want to use neural network, we have a problem because the input is fundamentally integer identifiers for user and items. And so we will need the concept of embeddings. So here is the core of the database is user number something interacted with item number something. If you feed those integers directly to a neural network, you would get nothing. It's just random noise. So you need to deal with those symbolic variables to treat those integers as symbolic variables and to find a good representation for them. So for recommender system, this could be the item IDs and user IDs, but we have exactly the same problem for neural net when we try to deal with text tokens for natural language processing, for instance, like characters, words, and bigrams. But it also happens when you have any kind of categorical descriptors. For instance, tags for your products. So it could be additional metadata on your product in the catalog, or movie genres, director names, the history of visited URL in the past. If you track the user activity to do a personalized advertisement, for instance, or skills on a resume if you are like a LinkedIn or Viadeo, for instance, or product categories, and so on. So for all those cases, we have this symbolic variable problem, and we will use the same notation. We will use the symbol S in a vocabulary V. So V is the set of all possible values, like the set of all possible item identifier in your catalog, or the set of all possible words in the English language. So it's a very large collection of discrete symbols. Typically, the cardinality is in the 10,000s to several millions or sometimes billions. So the natural way to find a vector representation, a numerical vector representation for those symbols, is to use the one-hot representation, one-hot encoding. So if you want to encode the symbol salad, for instance, what you can do is take all the words in the English language in the dictionary and assign them a specific dimension. So you have 1 million possible dimensions, for instance, and you would put zeros for all the entries except for the entries for the dimension that matches the symbol salad, and you set it to 1. So in that case, you get a very sparse vector that is discrete because the values are not continuous, they are 0 or 1. In a very large dimensional space, which has the size of the catalog or the vocabulary. Each axis has a meaning a priori, which is good because it's easy to interpret, but it's bad because it means that the distance between two vectors taken at random is always the same, whatever the meaning of the symbols that have been represented that way. It means that, for instance, the distance between the vector that represents salad and the vector that represents carrot is the same as the distance between salad and cake or roof or pig or whatever. So, which is a problem because it doesn't really capture the meaning of the concept. So instead, we might want to build vectors that encode the symbols into a continuous space that is a lower dimensional space with continuous values, not 0 and 1, but positive, negative values, and very rarely 0. So we want it to be continuous and dense. The dimensions in that space have no meaning a priori, and but we would like to have those vectors, the distances between those vectors, to capture some meaning relationship between the concepts. So this you can quantify this by computing the Euclidean distance or the cosine similarity between the vectors, or even just the dot product. So you can consider another way to see the embedding is to see it as a linear layer in a neural network, typically as an input, that will transform the one-hot representation of the symbol into the continuous space, the lower dimensional continuous space. So, and you do this transformation by just multiplying by a matrix, which is basically the embedding parameters. So W here, the matrix that defines the embedding, is actually initialized at random at the beginning, and the entries of that matrix are part of the trainable model parameters. So if you want to do this in Keras, maybe it's a bit too small, but it's very easy. It's just another layer that you put in your model, embedding. Takes integers identifiers for the symbols as an input, and they output a continuous vector that are fed to the next layer. So how to train those parameters? We have to plug that layer in the model and define the loss function that depends on the target that we want to predict. And basically, we will get a trainable architecture and use gradient descent as usual to adjust the parameters of the embedding automatically end-to-end. So let's talk a bit about architectures now. So if we take the original problem of predicting the number of ratings, the number of stars for that user I will give to item J in the catalog, what we can do is define two embedding matrices, or two embedding layers that are next to one another. One will take the integer ID as the input and will output the embedding vector for that user I, and the other one will do the same for the item. And the model will make a prediction by just doing a dot product of those two vectors, and we'll try to predict the rating, the number of stars, for instance. So this works only for explicit feedback. And to optimize the model, to fine-tune the model, we just need to minimize the difference between that dot product and the true number of stars that we have observed in the data. So it's a least square problem. And if you see the mathematical formula, it's exactly the same as the matrix factorization problem. So it's just a neural network way to present an existing model. But what is interesting in using a neural network building blocks is that you have a lot more flexibility. Instead of just taking the dot product as the way to capture the interaction between the user and the item, what you can do is plug a MLP with several layers. You just concatenate the two embeddings and then feed that to a feed-forward multi-layer connected perceptron, fully connected perceptron. And that network will output the ratings, the number of stars. And you minimize exactly the same loss function, but this time it's no longer the dot product, it's the output of the network that you compare to the ratings. And when you do that, you have a lot more flexibility, because now the size of the two embeddings can be different. If you have a lot more items than users, for instance, you might want to have a bigger embeddings for the items. And furthermore, you can integrate metadata about the users and about the items, and feed that into the network so that you have a hybrid recommender system. And what is also interesting for this is that if some of the metadata is also categorical, for instance, the name of the director for a movie, you can also build a new embedding for the director names and a new embedding for movie genres and so on. And so you have many embeddings as the input of the network, so you have a lot more flexibility than just a single matrix factorization model. And furthermore, if you don't have explicit feedback, you cannot use a regression loss as we did here. But what you can do is do a triplet architecture, for instance. So in a triplet architecture, you also have a user I that has seen a movie J, for instance. And what you do is you also pick up another movie that we call K at random in the rest of the database. So it's very likely that it's a movie that the user has never seen and will never see in the future, because there are so many movies, and most of them are negative. Those are movies that we will never see. We are not interested in them. So you can contrast a positive movie with a negative movie for a given user. And so you compute the two interactions by, for instance, in this case, by taking dot products, and you compute the difference between the two, and you want to make sure that the positive interaction between the user and the positive movie is larger than the negative interaction between the same user and another random movie. And you minimize that loss, that will maximize that difference. And at the end, you will train the embeddings of the model and make reasonably good ranking predictions. What is important here is that the V embedding that embeds the items is actually the same for the positive and the negative, same matrix. We just take different rows in that same matrix. So we train the same model parameters. So those are shared or tied parameters. And if you want to go deeper, you can do the same as we did previously, but we replace the dot product by a feed-forward neural network. And here again, the parameters of the two networks are tied, and in that case, we call them Siamese networks. And the loss function is very similar, and the whole architecture is called a triplet loss or a triplet network. This is not the only way to deal with implicit feedback. And for instance, this is the architecture by the YouTube team for making video recommendations. And here you see that as an input for a given user, you take all the embeddings of all the movies that user has seen in the past, or the videos that it has seen in the past. You take also the embedding of all the keywords that you typed in the search engine of YouTube. You add additional metadata like the geographic location, the age, the gender of the person, and you feed that to a feed-forward neural net. And the last layer of that neural net will basically compute a nonlinear embedding of the user at a given moment in time, in a given context. And based on that, you can compare that to all the embeddings of the items and to try to predict the next movie that user is going to watch. And by doing a gradient descent on that loss function, which is just a logistic, basically the output is just some kind of logistic regression, a log loss. Then you can train all the model parameters, the embedding for the queries, the embedding for the movies, and all the parameters of the intermediate model. So it's very powerful, and it's very flexible because you can mix and match many different kinds of data together, heterogeneous. So it's a bit of the philosophy nowadays to embed all the things. Like discrete variables, you can use linear embeddings. Images and sounds, you can use convolutional neural network. Most of the time, in that case, you would like to use pre-trained convolutional networks. For instance, on the album covers, or on the, as we've seen previously, on the pictures of locations, if you sell travels and so on. Sounds might be useful for streaming, and they have experimented with that at Spotify. I don't know if it's in production or not. You can also do sequences of discrete tokens with recurrent neural network. For instance, if you type a query, the order of words might matter. So just doing an average of the query keywords might not be a good idea. Maybe a recurrent net might be better, or a convolutional neural net. And you can also embed like more structured input. Like for instance, for molecules, you can take the graph representation of a molecule and use a graph convnet to embed it into a vector space. And obviously, we're not very interested in recommending molecules, but it's just to highlight that we have a lot more flexibility when we do that. And furthermore, we also the deep learning ecosystem comes with a lot of additional tools like optimizers, like Adam, regularization mechanism like Dropout, and many open source implementation that are very easy to get started to experiment basically on your data and to do this iteration. So my main point here is this trend to move toward deep learning tools will give you a lot more flexibility to build recommender systems. Thank you very much for your attention.